But the thing is, if you all have not yet received it, I will talk to the IT people in SLTC and then see what I can do. Okay. So have you all checked in the IMS system? Did you all check it? Even at least yesterday also, have you all checked it?
Not yet, madam.
Not yet. Can you all just do me a favor today after the lecture? Can you all go to that one and then see whether you all can receive it or not? So then I can talk to SLTC and then see what I can do. Okay, can you all do that for me today?
Okay, madam.
Okay. Do we need to wait for some more time? I think I have got 3 students and one got disconnected. One got disconnected. Okay. Altogether, I think it's only like 6 students, even that they have not uploaded how many students are participating for this lecture, because I can see in the portal there are like somewhere around 18 students, but 18 students normally do not get into this lecture. So I'm pretty sure, since this is an elective, is this a compulsory subject to you?
Yes, madam. This module only have to for the textile technology students.
Okay, so in your batch, how many students are there, textile technology?
We have 6 students.
6 students. Okay, so today with me, I have got 4 students. I hope the other 2 will join at least within next few minutes. So until then, I will start the lecture. Please do check today whether you all can get the things which I have uploaded to the LIMS portal, LIMS portal. And then if it is not there, uh, may I share my phone number with you all, so then at least you all can send me an text message. So I will share it with Lahiru. Okay. Okay, I have shared my number with Lahiru. Lahiru, please let me know by today evening whether you all can see the lecture materials which I have uploaded to the web portal. All right. Okay, so shall we start the lecture now? Okay.
Excuse me, madam.
Yeah.
Madam, lecture notes still not visible in the
It's not visible.
LMS.
Okay, it's not visible, right? Okay, sure. So I will check with the SLTC Information Technology Department and then see what I can do. I think I have uploaded it in 2 places. Since I don't know how to share, I have got the link also. But the thing is, I can't share the link with you all. That was the main problem. So I need to check with them how to share the things with you. Okay, so for today, let us start the lecture. So if I go back to the the syllabus of this module, I may share my presentation. I may share the syllabus with you. Okay, so in here, I hope you all can see my screen. So in here, in the syllabus, we need to discuss about the nanotechnology as the introduction. So during the last lecture, we have talked a little bit about history of nanotechnology. And also I think today, and also I have given a brief introduction to what nanotechnology means. And also we have discussed about a methodology that a group of scientists have used to come up with a special fabric material, and that special fabric material is having this mosquito or bugs repellent property. And also in that video, they discuss how they have incorporated this specific mosquito repellent chemical into a textile. So when you mainly incorporate special chemicals to get specific functional properties, there are different methodologies we can follow. So some of them have used coating technologies where they coat the textile material with these active chemical ingredients. But the main disadvantages in those methodologies are sometimes, now if you talk about a mosquito repellent kind of a chemical, those are highly evaporative. So these evaporative type chemicals, what happens is with time it will get evaporated from the textile substrate, so then its activity will get reduced with over the time. And also these coatings might be having very low chemical interactions with the textile material. So then what will happen is when you wash off the garment, these coatings will get washed away. So the approach that specific research group has taken was they have incorporated this chemical, embedded this chemical into a yarn using a normal yarn spinning methodology. So in there, they have used a cotton or a regenerated cellulose spinning methodology where they have incorporated this chemical with a certain waxy material. So the main purpose of the waxy material and the main purpose why they have incorporated the chemical during the yarn spinning process itself is, so then these chemicals will get inside to the yarn, so then it will be having a certain protection over the time. Otherwise, what will happen is if it is on the surface, just on the surface as a coating, these chemicals will get evaporated, so then its activity will get reduced over the time. So just by incorporating it inside the yarn, and also what happens is with time it will retain for a certain longer time duration. And also the main purpose of having a waxy kind of a material with the chemical is, we all know these waxes have a certain melting point. So these waxes, if we can get into the nanoparticle form inside the yarn, these waxes, the surface area would be high because it is in the nanoparticle form. So when the surface area is high and also being the waxy material, where they have these active ingredient encapsulated inside these waxy particles. Now, when it touch your body and when it come to a certain temperature, these wax particles will get melted. Just hold on a few minutes because it's heavily raining. I think I need to cover the. Am I audible to you?
Yes, ma'am.
Okay. So in there, what they have done was they have incorporated or encapsulate these active chemical ingredient into a waxy nanoparticles. So the main purpose of having waxes is, and also embedding it into a nanoparticle form of a waxy particle is, these waxes have a melting point. ඒ කියන්නේ අපි දන්නවා ඒක melt වෙනවා at a certain temperature. So when these get melted, what happens? The active ingredient inside these waxy particles will get released. So that means it will be type of a engineered release. That means it does not get released. That means it will not get released at any time. It will get released on a specific period only. That specific period will be decided by certain mechanical and chemical properties of the waxy particles that they have used. So they have used the melting temperature. So we have discussed about that work as well. So today we will try to learn about what do you mean by different fabrication. Now, when it comes to the nanoparticle, as I have explained during the last lecture, people need to have a methodology to fabricate or to produce nanoparticles. And also, there are certain physical laws which are active in the nano range and the micro range. So sometimes these physical laws at the micro range and the nano range, the same material, when the dimensions change, taking the same principle of the physical laws, amount of forces which act upon nanoparticles might vary when you compare it with the micro range particle. Okay, so and also now for today we need to learn a little bit basic about atomic structures and what do you mean by a molecule. And also, we will look at using certain chemical molecules, what are the approaches that we can take to form nanoparticles using either bottom-up or top-down approaches. Okay, so when you form these nanoparticles also, we need to look at what are the forces act on these molecules or atoms for them to get into the nanoparticle form. Okay, and also let's look at when you take nanostructures can be of different dimensions. So when you talk about different dimensions of these nanoparticles, what do you mean by a what do you mean by a zero dimension nanoparticle? What do you mean by a one dimensional nanoparticle? Okay. Okay. Is my voice is lagging? Uh, is it now okay? Because you just have to bear with me for a little bit because in here it's heavily raining. So when it is raining, there could be certain discontinuities in the internet connection. I cannot help that. I hope you are audible to you. Okay, so let's directly go to the presentation. All right. Okay, so I think history of nanotechnology. This is where we have stopped during the last lecture. Hope you all can see my screen. So, so in here we talk about the Damascus sword. We talk about different paintings where they have done. And these paintings, when they have analyzed these paintings, they have observed that painting consists of a same type of a material, but that material give different colors. So when they analyze these paintings, they have identified these paintings consist of silver particles. So then we need to mainly identify how come the same material being a silver material, how that material can give different colors. So those are a few main reasons why people use nanotechnology. And also, if I can recap what we have talked about this. Hello. If we recap what we have talked about this liquor gas cup. So liquor gas cup also now by using or kind of like with the way the light interact with this liquorous cup. So how does the light get reflected depending on that? This liquorous cup, when you hold it into the when you hold it, you may see different colors. So that is the mystery behind the liquorous cup. So today And also, I think today we will talk about the nanoscale. I hope most of y'all might have followed your O-level, A-level syllabus, and then within this O-level, A-level syllabus, they might talk about the nanoscale. So if we take the nanoscale, a nanometer is 10 to the power minus 9th of a meter. So this range is normally not visible to our naked eye. The maximum visible range to our naked eye is 10 to the power minus 4th of a meter. Okay. So if I take some example at different scales of its dimension, now if we take a human, normally a human might be in a scale range of 1 meter. So which is visible to our naked eye. And if we take our hand, our palm area, like given in this image here, the size would be somewhere around 10 centimeter. And then if we further go downward, if we take a human hair, this human hair could be somewhere around 100 micrometer. So even a human hair without any microscope, we can still observe it using our naked eye. Okay. So when it go beyond 100 micrometer, that is, if we go beyond 10 to the power minus 4th of a meter, say for an example, if we take a red blood cell. So we all know the red blood cells, we cannot observe it using our naked eye. So for that, we normally use a microscope. So we call these as microscale. Less than 100 micrometer, we call it as a microscale. So even the red blood cell, we can observe it using a microscope. So if we further go downwards, if we take a bacteria, which we cannot observe using our naked eye, bacteria which normally grows in these biological sources, say for an example, a bacteria species such as E. coli. So the size of these E. coli bacteria would be somewhere between 400 nanometers to 1 micrometer. So even this one could be magnified and could be observed using a normal optical microscope. But when we go further downwards, like a normal coronavirus or any type of a virus, where the size is lower than a normal bacteria, the size would vary somewhere around 300 nanometers to 100 nanometers. So when we go beyond the 400 nanometers, we cannot see it or we cannot observe it even using an optical microscope. So the main reason behind why we cannot observe it using an optical microscope is in the optical microscope, for the magnification purpose, we use light, visible light. So if we take the visible light, the wavelength of that visible light would be somewhere between 800, 900 nanometers to 400 nanometers. So that is the visible range to our naked eye. So if we have particles which are less than 100 micrometer, which we cannot see using our naked eye, we use an optical microscope. So in the optical microscope, we have lenses. So in these optical microscope, what they do is they have lenses. They take the visible light rays. So that visible light rays goes through these lenses. So then it will do the magnification. But if we take a particle or a material which are lower than 400 nanometers, so that is those particles are even lower the wavelength of a visible light. So then in order to magnify these very small size particles, we cannot use an optical microscope. because in the lenses which are used in the optical microscope, they can do only the magnification or the focusing for the visible light. So if your particles or the materials are less than 400 nanometers, we cannot use a optical visible light beam to do the magnification. So beyond the 400 nanometers, we call it as the nanoscale, but the real nanoscale start from 400 nanometer to 1 angstrom range. So in that range, we have special equipment. We, instead of the visible light rays, we use electron beams for us to do the magnification, because these electron beams, the wavelength of these electron beams would be in the angstrom level or in the 1 nanometer range. So then these electron beams would do the magnification for us to see any material which is beyond 400 nanometer range. Okay, so that is why we say beyond 100 nanometers, that is any material which are smaller than human hair, we cannot see it using our naked eye. But the materials which are between 100 micrometer to 400 nanometers, instead of using our naked eye, we can use optical microscope magnifying equipments for us to magnify them and observe them. But if you go beyond the 400 nanometer range, we cannot even use an optical microscope. So in order to observe the particles at that scale, we need to use certain specific microscopic units. So these microscopic units mainly uses electron beams as their main observing source, not the optical beam. All right. So if we further takes the how the scale works, now inside your red blood cell, we all know there's a certain thing called hemoglobin. So if we take the size of a hemoglobin unit, so these are molecules get together in this hemoglobin. So the size would be somewhere between 50 nanometers to 10 nanometers. All right. And then if we take a glucose, we all know glucose molecules, what we have in our sugar, and also the carbohydrate type molecules which we have in starch or rice. So at that scale, it would be even less than 1 nanometer. So when we further go beyond the 1 nanometer range, so it comes the angstrom range. We call this range as the angstrom range. Normally a hydrogen atom, size of a hydrogen atom would be a 1 angstrom. So hundreds of angstrom would be a 1 nanometer. So then thousands of nanometers would be a 1 micrometer. All right, so that is how the scale works. So now you all know what is the visible range to our naked eye, what is the range, that size range that we can zoom and magnify it using an optical microscope. And so after that, when you go beyond or lesser sizes beyond the 400 nanometer range, we need to use specific equipment to do the magnification. So in here, this image mainly shows you the microscopic image of a human hair and a magnified image of a butterfly wing. So this butterfly wing, you can see there are certain kind of like a scaly structure on top of that butterfly ring. So if we take the scale, this scale is very, very low. So these tiny ridges could not be observed using an optical microscope, because these ridges sizes, the distance between two ridges would be less than 400 nanometers. So for that, in here, they have used an scanning electron microscope to observe this butterfly wing. Even in here, you all can see in our human hair, there are certain scaly structures. These scaly structures could not be observed using an optical microscope because the size of these scales are very, very low, where you cannot magnify them using a normal visible light beam and a normal optical lenses. So in this um, scanning electron microscope image, we can clearly see these butterfly wings have these ridges, and even our human hair have this scaly structure. So this is how the nanoscale works. Anything that you need to get clarified from me, it should not be in English. You can ask me even in Sinhala. Okay. So up to now, is it clear? Can I move forward? Okay, it's clear. So let me move forward. Mm, okay, now when it's come to the nanoparticles, there are different methodologies that we can use in order to form a nanoparticle. So there are mainly two types of methodologies. Two main types of nanoparticles processing methodologies are termed as top-down and bottom-up approach. So if we take the nanostructured materials, in order to fabricate this nanostructured material, we can start from a bulk material, and using certain grinding, certain laser ablation processes, we can grind these bulk or large size material into small scale. So we call this approach as a top-down approach. All right. Or else what we can do is we can use the bottom-up approach. So in the bottom-up approach, what happens is atoms or molecules assemble themselves in a way where it will get into a nanostructured material. Okay. So if we further discuss about this, bottom up involves the addition of atoms and molecules into nanoparticles. Okay, there could be certain chemical bonding happening, certain molecular bonding happening, certain level of self-assembling happening. So in there, we need to mainly discuss a little bit about what an atomic structure is. I hope you all can remember what you all have learned during your school time. So these atoms have nucleus and electrons, and when they have nucleus and electrons around the nucleus, so depending on the electron configuration, the energy orbital levels, how this bonding is taking place. So these things we learn a little bit during our school time. But here today, I have taken few videos where I will try to recapitulate your knowledge on about what atoms are and how the electrons are moving around the atom. So before we move into the next slide, let's have a look at that one a little bit. Okay, and also when you take the top down process, in there what they do is large materials can be broken down into small nanoscale particles. All right. So in summary, both of these types materials could be processed to the nanoscale, and these nanoscale are called nanostructures, and these nanostructures also could be of different dimensions. You all know in any material we have three dimensions: x direction, y direction, and z direction. So when we have these dimension, depending on the range of the scale at each of these dimension, these nanostructures could be further classified into 0 dimension, 1 dimension, 2 dimensional, or 3 dimensional material. So let's talk about that as well. So before we move on to how these specifically how this bottom-up approach is taking place, where atoms or molecules get together to form a nanostructure, let's have a look at what do you mean by an atom and how the electrons are moving around these atoms. All right. Okay, I will share my screen. Just give me 2 minutes.
Let's take a closer look at atoms. Atoms are
Okay, I will share a video with you. I'm pretty sure you have learned about these atomic structures before. But before proceeding in this lecture, I think it is my responsibility to teach you what an atom means and how the nucleus and electrons are there inside an atom. Okay, so I will share this video. Just follow the video. Anything that you cannot understand, I will explain it further. Okay.
Let's take a
Can you all just let me know whether the video is audible to you?
closer look at atoms.
Is it audible? Is the video audible to you?
Yes, madam.
Okay, so let's go through this one.
Let's take a closer look at atoms. Atoms are the building blocks that make up everything, all stuff everywhere. Here I've got some drawings. This is table salt, a solid. Here's water, a liquid, and finally oxygen gas. And what we're looking at here is what we'd see if we could take these.
Can you all see the video smoothly? Is it breaking? Okay, so
Think. All stuff everywhere. Here I've got some drawings. This is table salt, a solid. Here's water, a liquid, and finally oxygen gas. And what we're looking at here is what we'd see if we could take these three things and zoom in zillions and zillions and zillions of times. And if we could look at these closely enough, we'd be able to see the atoms, these little building blocks that make everything up. Now, atoms aren't really little colored circles, but it's a good way to think about them, and it's the way we'll usually draw them when we're learning about this stuff. Atoms are super tiny. They are so tiny, it can be really hard to wrap your head around how tiny they are. Here is something that might help you think about this. Take a piece of paper. Look at how wide it is here, all right? This is so incredibly thin. Now, atoms are so small that it would take 1 million atoms lined up next to each other in a row to be as thick as this tiny width of paper. That's how small atoms are. Now, what I want to do now is look even closer at an atom. Let's take one of these atoms here and zoom in even more so we can see what's inside of it. Here's a magnified view of one atom. It's not a perfect representation of exactly what an atom would look like, but it's close enough for right now. And check this out. The atom itself is made up of even smaller things, right? So that we said atoms are like the building block for all of stuff. But then if you look at an atom, it has even smaller building blocks that make it up. So in the center of the atom is something called the nucleus. And the nucleus is made up of two tiny particles. There are protons, which I've drawn as red circles here, and then there are neutrons, which I've drawn as blue circles. Nucleus is here in the middle of the atom. And then on the outside of the atom, there are these little black circles that I'm using to represent electrons. The electrons you'll see are connected to these sort of oval paths, and I've drawn these in to show that the electrons are constantly moving. They're flying around the outside of the atom at an incredibly high speed, whereas the nucleus stays solid here right in the middle of the atom. Now, electric charge is very important when we're talking about atoms for a number of reasons. Protons have a positive charge. A proton has a charge of 1 plus. Electrons, on the other hand, have a negative charge. One electron has a charge of 1 minus. Now, neutrons, they don't have an electric charge at all. They have a charge of 0. And neutral is a word that we use to refer to something that doesn't have a charge. So neutrons sounds a lot like neutral. Now, positive and negative charges attract. Remember that? Opposite charges attract. And that has important consequences for how this atom works. We said that these electrons are flying around the outside of the atom. They're moving really fast. So why don't they just fly out into space? Well, the reason why is because the negatively charged electrons are attracted to the positively charged protons. So the protons kind of pull the electrons in. They keep them from just flying away. But the electrons are moving around so fast that they're not able to actually pull in here and actually touch the protons. So that's why they keep staying on the outside and don't just crash in here and all touch the protons. Now, sometimes people ask, well, neutrons don't have a charge. Why are they important at all? Well, it seems that neutrons help keep all of the particles in the nucleus strongly connected to each other. Now, electrical charge is important. Something else that's important with atoms is what their mass is, how much they weigh. So in order to figure that out, we have to look at the mass of the various things that make up the atom. Now, a proton and a neutron are very, very similar in size and in mass, and they both weigh about this many grams. Look at what a tiny number this is, right? There's a decimal place all the way over here. This is a number that it's best to represent in scientific notation instead. But however you write this, it's a really tiny, unwieldy number. So scientists came up with another way to measure the mass of a proton or neutron, and that's using a unit called the AMU, the atomic mass unit. And they said, okay, 1 proton or 1 neutron weighs about 1 AMU. That's a lot easier to use than this measurement here. So proton or neutron weighs about 1 AMU. An electron, on the other hand, is much, much, much smaller than a proton or a neutron. It weighs only 0.000549 AMU. So a tiny fraction of how much a proton or a neutron weighs. For this reason, when we're talking about the mass of atoms, which we'll talk about later on, we usually add up the protons and neutrons to find out how many AMUs the atom weighs. And then we usually don't even worry about the electrons at all because they're so tiny. They don't really have much of an influence on how much an atom weighs. It's like when you get on a scale to weigh yourself, you don't worry about the ring you're wearing or whether you're wearing a necklace or something, because those things are just so tiny, they weigh so little compared to how much you weigh that it doesn't really influence your weight. So protons and neutrons, 1 AMU, and electrons, a tiny fraction of that. Now, I said that the atom, the way it's drawn here, isn't a perfect representation of what atoms would actually look like. We'll talk more about that later, but there are 2 things that I want to bring up for right now. The first is the electrons and how they move. This drawing might make you think that the electrons are spinning around in nice circles on the outside of the atom. That's actually not what happens. They're buzzing around much more randomly, kind of like hyperactive flies all over the place. We'll talk more about that later. The second thing has to do with the size of the nucleus and how far the electrons are from it. If this were a real atom blown up many, many times, and the nucleus were the size of a grape, the electrons out here would be almost a mile away. You have this grape-sized nucleus, and a mile away would be the electrons spinning on the outside. So that means that most of an atom is actually empty space. Anyway, now that we've talked about what an atom looks like and the particles that make it up, we can go and discuss some of the characteristics that we can use to describe atoms. These are things like atomic number, mass number, and net charge.
Okay. Okay. Have you all got an idea about what an atom is? Are you all with me? Can you all hear me? Okay. Navodya, can you kindly let me know now based on that video which I have shared with you? Okay, so in there they talk about something called an atomic mass unit. So in that 1 AMU, what would be the gram? How do you define an 1 atomic mass unit? What is the weight of a 1 AMU? Navodya, are you with me? Hello? Hello, Navodya? Okay. So if Navodya is not there, I'm not sure why y'all are not responding. Can Harsha please answer my question? If you take a 1 atomic mass unit, so in a 1 atomic mass unit, what would be the weight of a 1 atomic mass unit? Yeah, Lahiru has given me the answer. Harsha? I think are you all listening to this lecture from your personal computers, or are you all in a kind of like a group and where you participate for the lecture? Lahiru, are you all at, I hope you might not be at SLTC, you might be joining the lecture with your personal computers, isn't it, Lahiru? If you can just answer me through the chat. Okay, personal devices. All right. So I don't know why Harsha Navodya is not responding. I know Lahiru is there. Naveen, hello.
AMU is equal to the number of protons in the nuclear, and we can
Yeah.
we can multiply by the weight of the proton. We can.
Yeah. 1 AMU means Naveen. It is kind of like a single unit that they use to describe the weight of an proton or a neutron. So protons and neutrons, they have the weight unit as 1.67 to the power minus 24 of a gram. All right, so that number normally referred to as a 1 atomic mass unit. Okay, so protons and neutrons have that weight, but when you talk about the neutrons, when you talk about the electrons, the weight of an electron is very, very less. It is somewhere around 0.005 something of a neutron. So the weight is very, very low. So most of the weight of an atom the contributions are from the neutrons. All right. And also they have talked about there's a nucleus, the charges of the protons and neutrons. Protons are positively charged, neutrons does not have any charge. And also when you have electrons, electrons are negatively charged, electrons spin around the nucleus. And when you take the distance between the nucleus and the electron spin orbital, the distance is very high. Most of the spaces inside the atoms are empty space. So that's what all about the video which I have shared with you. And this is just to give you an idea about what an atom is, because in our next few slides, we need to talk about the bonding of these atoms and how these atoms get into a molecule and how these molecules get into nanoparticles to do the nanoparticle formation. All right. And then again, now when we have these atoms and the electrons orbiting around it, we need to talk about different energy levels that an atom has, because these energy levels plays a very big role when it's come to the bonding, and when it's come to the bonding between each of these atoms, it plays a very important role. What are the bonding types that they are using, different types of bonding they are using, and with that bonding type, it majorly contributes towards the nanoparticle formation. We talk about the bottom-up approach of starting from a single atom or starting from a single molecule and then self-assembling these atoms or molecules into a single unit of a nanostructure. So in order to understand that, we need to know some basic principles about the atom. So next, I will show you how these electrons configure inside an atom. So then you talk about energy levels, because further into this lecture, when we talk about different analytical methodologies, mainly to characterize some of the key functional parameters of our nanoparticles, then of course we need to know about atomic structures, specifically the electron energy levels, how these electrons orbits around the nucleus, and what do you mean by different energy levels, how do you name those energy levels, those things we need to know. So I will share another video, just have a look at this video and then try to understand the nomenclatures that they use or the naming system that they use for these different energy levels. All right. I will share another video with you.
In this video,
Okay, just go through this video very carefully, just listen very carefully and try to understand what is in here. So then you will have a better understanding about the electron configuration inside an atom. So this configuration and the understanding of these configurations are very much important for us to take this lecture forward, because there will be different things that I will be teaching to you. These teachings will mainly depend on these electronic configurations as well. Okay.
in this video, I'm going to give you a simple introduction on how to write the electron configuration.
Just let me know whether the video is audible. Is the sound clear to you? Naveen, is the sound clear?
Madam, sound is clear, but the video is not clear.
Yeah, video still, I think it's a black screen.
Yes.
I will start the video.
In this video, I'm going to give you a simple introduction on how to write the electron configuration. of an element. So let's talk about nitrogen. So how can we write the electron configuration for an atom of nitrogen? So that's how nitrogen looks like on a periodic table. So the higher of these two numbers is the mass number, and the smaller of the two numbers is the atomic number, which is an integer.
So in here, I just want to disturb a little bit. They have taken the nitrogen as the atom. So they have taken this as the atomic number 7. 14 is the mass number. All right.
This is the mass number, and the smaller of the two numbers is the atomic number, which is an integer. Now, what we need to know is that in the first energy level, you have the 1s sublevel.
So from this one, they will be just explaining different energy levels and how these energy levels are named. Okay, so these are standard energy levels and the naming system is also standard.
In the second energy level, you have the S and the P sublevels. In the third energy level, you have S, P, and D. Now for nitrogen, this is as far as we need to go. The S sublevel can hold 2 electrons, and the P sublevel can hold 6, and D can hold 10.
Okay, so in here, we know there are different energy levels. So these energy levels might be have different orbitals inside these energy levels. So these orbitals could be named as s orbitals, p orbitals, or d orbitals. So in the first energy level, they have only a one s orbital. In the second energy level, they have s energy level and a p energy level. In p orbital, s orbital and a p orbital. In the third energy level, they have a s orbital, p orbital and a d orbital. And also when you take s orbital, p orbital or d orbital, in the s orbital, it can occupy 2 electrons. In the p orbital, they can occupy 6 electrons. In the d orbital, they can occupy 10 electrons. All right.
Now you want to write the electron configuration until you get a total of 7. Now for an atom of nitrogen, it contains 7 protons and 7 electrons, but we're focused on the number of electrons because we're writing the electron configuration.
Okay, so in here, this nitrogen atom, they have an atomic number 7 and a mass number 14. So if you can remember, we learned about the mass number is the number of protons and neutrons in the system. So if the atomic number is 7, that means the number of proton inside the atom is 7. So it might be having another 7 neutrons. If the number of protons are 7, that means the number of electrons in the atoms is also 7. So now what they are going to do is they are going to give you the electron configuration. That means how these electrons are distributed among different energy levels. So in here they are not worried about the number 14 because it is the mass number, but they are worried about the number of electrons in the atom. So it's the number 7. So number 7, now they will distribute them among different energy levels. So the distribution of the electrons among different energy levels basically talks about the electron configuration of a specific atom.
For ions, that number could differ, but for atoms and electrons. But we're focused on the number of electrons because we're writing the electron configuration. For ions, that number could differ, but for atoms, you just need to focus on that number. So then,
okay, so in here you heard a term called ions and an atom. We all know atoms are neutrally charged. That means there are no charge, positive or negative. But an ion normally it might be having a positive or a negative charge. So in here, when you take an atom, if the number of protons are 7, the number of electrons are also would be the 7. So for an atom, if the structure is given like this, that means they are having 7 electrons. But if it has a charge in this atom, we cannot take the number of electrons as 7. Okay, this has a charge. All right.
Configuration. For ions, that number could differ, but for atoms, you just need to focus on that number. So the number of electrons in this problem is 7. So here's what we need to do. First, start with 1s. So I'm going to write 1s2 because s can hold up to 2 electrons. Next, move on to the 2s sublevel. 2s can also hold 2 electrons. And then after 2s, you want to go to 2p and then 3s. Now, 2p can go up to 6. It can hold 6 electrons, but we only need 3 more. Because if you add the exponents, 2 plus 2 plus 3 is 7. So once you get up to this number for atoms, you can stop. This is the electron configuration for an atom of nitrogen.
Okay, so in here, if I further explain it, he basically explained how these electrons fills into the energy levels. There's a pattern how electrons fills into these energy level. It need to start from the first energy level first. So in the first energy level, we have only a 1 s orbital. So in an s orbital, we all know it can occupy only 2 electrons. So if you write that one, it has first energy level, s orbital, there are 2 electrons. So after that, it need to go to this line. That is the second energy level. So in the second energy level, the filling would happen first at the s energy level. So second energy, s orbital, it has 2 more electrons which you can occupy. So now altogether, you have filled 2 plus 2, 4 electrons. There are 3 electrons remaining. So first energy level, you first fill the s orbital and then you go to the second energy level. So in the second energy level, you first fill it to the s orbital. And when this is filled, you go to the third energy. So this is the first filling at the s orbital, and then this is the sequence. The second energy s orbital, and then it need to go to the second energy p orbital. After filling the s orbital, you need to go to the p orbital. Okay, that's why he has written this arrow. First, second, this is the third level of filling. So in the third level of filling, first you need to go to the second energy level p orbital, and then you need to go to the third energy level s orbital. So that's the sequence. So now this nitrogen atom, it has 7 electrons altogether. We have already filled first energy level s orbital, second energy level s orbitals. So totally we have occupied already 4 electrons. So 7 minus 4, 3 electrons are remaining. When you go to the p energy level, we have just talked in the p orbital. It can occupy 6 electrons, but we only have 3 more remaining after you already distribute 4 electrons. So the next filling would be the second energy level p orbital, but you put only 3 because it will add up to 2 plus 2 plus 3 equals 4. So this is how the electron configuration of a nitrogen atom is. Okay. So we will further have a look at this one.
You can stop. This is the electron configuration for an atom of nitrogen. Now let's try another example. Let's write the electron configuration for aluminum. You can try it if you want to. So we're dealing with an atom of aluminum, which has 13 electrons. So you want to write the configuration up to 13. Now we're going to set it up the same way. Now, if you want to, you can add the 4th energy level, which contains 4s, 4p, 4d, and 4f.
Okay, just pay an attention to here. Now, for the last example, we have talked about the first energy level, second energy level, third energy level, because it can go up to the first energy level and second energy level. But in any atoms, we might be having a fourth energy level as well. So in the fourth energy level, the orbitals are like you have s orbital, you have p orbital, you have a d orbital, as well as you have a f orbital. So let us see what are the number of electrons that you can put into the f orbitals. We know s orbital you can put 2, for the p orbital you can put 6, for the d orbital you can put 10.
Now let's put these numbers again. F can hold up to 14 electrons.
F14.
So we're going to start with 1s. So that's 1s2. And then after 1s, we have the 2s sublevel. So this is going to be 2s2. And then we need to move on to 2p, then 3s. So p can hold up to 6, and s can hold up to 2. So if we add the numbers 2 plus 2 plus 6 plus 2, that's 12. We only need one more. So after 3s, we need to move on to 3p. Now we don't need to go up to 3p6. We only need one more. So we're going to stop at 3p1. So if you add 2 plus 2 plus 6 plus 2 plus 1, that will give you a total of 13. So this is the ground state electron configuration of an atom of aluminum. Now what about ions? Let's say if we want to write the electron configuration of the Fe2+ ion. How can we do so? Now on a periodic table, Fe has an atomic number of 26.
Okay, so just to disturb a little bit here. Now, the last two example, we have looked at how we write the electron configuration of a neutral atom. So now in here, he will be explaining how you are going to write the electron configuration of an ion. So in ions, atoms have a certain charge. So in this charge means they might have lost certain number of electrons, or these atoms might have a certain additions of electrons. So that's why we call them as an ion. So let's see how he is going to write the electron configuration of an ion. Fe, ion 2+. Okay.
If we want to write the electron configuration of the Fe2+ ion, how can we do so? Now on a periodic table, Fe has an atomic number of 26 and an average atomic mass of about 55.85. So an atom of iron metal has 26 electrons. So what about an ion of Fe? Because the charge is +2, that means that the atom lost 2 electrons. So therefore,
so that is, if an atom has a positive charge, we all know protons are having positive charge, electrons are having a negative charge. If your atom is having a positive charge in a neutral atom, what need to happen? Number of protons and number of electrons are similar. So it has a neutral charge. But in an ion, if it has Fe ion, this has a 2 positive charges. So that means it has lost some of their electrons. So the atom is not neutral. All right.
because the charge is +2, that means that the atom lost 2 electrons. So therefore, the Fe+2 ion has 24 electrons. It has 2 less than this number. So we're going to write the electron configuration based on the number 24. So let's make our list again. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. S can hold 2, P can hold 6, D can hold 10, F can hold 14. So we're going to start with 1s. So that's going to be 1s2. And then we're going to move on to 2s. So this is going to be 2s2. And then we're going to go to 2p, then 3s. So it's going to be 2p6, and then 3s2. Now after 3s, we got to move on to 3p, then 4s. So it's 3p6, and then 4s2. By the way, before you write the electron configuration of Fe plus 2, it's better if you write the electron configuration of the parent atom, and then from that, write the electron configuration of the ion. So I'm going to focus on 26, and then I'm going to adjust it to 24.
So in here, pay attention here. So he has just talked about when you have an ion, that means a positive charge atom. So it is better to first write the electron configuration of the parent atom. So in the parent atom, you are having 26 electrons, but in the Fe2 plus ions, you have 24 electrons. So before going into write the electron configuration of the Fe ion, he is going to write the electron configuration of the Fe parent atom. All right.
Write the electron configuration of the ion. So I'm going to focus on 26, and then I'm going to adjust it to 24. So right now, we have a total of 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is another 10. So we need 6 more electrons to get to 26. So after 4s comes the 3d sublevel. Now d can hold up to 10, but we only need 6 more. So this is the electron configuration of Fe, but not Fe plus 2, because we have a total of 26 electrons. Now from this expression, you want to write the electron configuration of Fe2 plus. So you need to remove 2 electrons. The question is, which 2 electrons do you remove?
Okay, so now here comes the problem. Now you all have distributed all the electrons into the specific energy levels by considering the parent atom. So in the parent atom, it has 26 electrons. But now we need to know when it's come to an ion, which is having a positive charge, from which energy level that 2 electrons need to be taken out. So let's pay attention to that one.
2 plus. So you need to remove 2 electrons. The question is, which 2 electrons do you remove? Now what you need to do is remove electrons from the highest energy level. So that's from the 4th energy level. So you're going to take off these 2 electrons. So we could therefore write the configuration for Fe2 plus as 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, or you could just omit it, and then 3d6.
Okay, so have you noticed that one? When you write the electron configuration, what is the most away energy level is the 4th energy level. So if you are to remove the 2 electrons, we just cannot move it from energy levels which are further close to the atom. So if we take the atom like in here, the most closest one is first energy level, and then the 2nd energy level, 3rd energy level, and the 4th energy level. So up to 4th energy level, the electrons are filled in this electron configuration if you consider the parent atom. So the last energy level it has is the 4th energy level, s orbital, 2 electrons. That is the outermost energy level. In here, they have only the s orbital. So in order to remove 2 electrons, the electrons could kick off from the furthest away energy level, that is the s orbital, 4th energy s orbital. So from the s energy level, they have removed the electrons. So this should be the electron configuration of the Fe ion.
Now, if you were to write the configuration based on this number, and if you didn't do this step first, you might be inclined to write 4s2, 3d4, and it won't be correct.
Now, can you see? can you see if you do not consider the parent atom and if you start writing the electron configuration just by looking at the number of electrons in the ions, you might end up writing the electron configuration as to distribute 24 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4, which is not correct. So if you are to think about the electron configuration of an atom, first you need to think about the electron configuration of the parent atom, and just only by having a look at the parent atom electron configuration, you can remove the electrons, so then it will best fit the electron configuration of the ion. All right.
3p6, 4s0, or you could just omit it, and then 3d6. Now, if you were to write the configuration based on this number, and if you didn't do this step first, you might be inclined to write 4s2, 3d4, and it won't be correct. So when you're dealing with transition metal ions, it's best to write the configuration of the parent atom first. And then if you have a positive charge, simply take off electrons that's equal to the charge, starting from the highest energy level. Now let's move on to our next example. So we're going to deal with chlorine. So here's the information that you need to know for chlorine. Now what I want you to do is write the electron configuration for the chloride ion. Go ahead and try that problem.
Can you all also try it if you have a pen and a paper with you? Chlorine ion.
Now for chlorine, we really don't need the fourth energy level. So let's start with this. We need to get up to 17, and then we're going to add 1.
So, okay, so in here, this is a negative ion. That means it has more electrons. So the total number of protons in this atom is 17. So in order to have a neutral atom in the parent chlorine atom, it might be having a 17 electrons. But the chlorine ion present in here has a negative charge. So that means there could be 1 electron additionally given to this chlorine atom. So then it would be having a negative charge. Okay, so let's see how he is going to write the electron configuration of this atom. Sorry, ion.
Chlorine, we really don't need the fourth energy level. So let's start with this. We need to get up to 17, and then we're going to add 1. Chloride has a total of 18 electrons. Now for this one, we can just go straight to 18. We don't have to start from 17 and add 1. You could do that if you want to, but you don't have to, because chlorine is not a transition metal. So I just want to rephrase this one more time. For transition metals, it's best to write the electron configuration first, and then subtract the appropriate number of electrons based on the charge. For elements that are not transition metals, and if you're dealing with ions, you can go straight to this number.
Okay, so in here, what we want to highlight is, now there are things called transition metal ions. So if you are to think about the electron configuration of a transition metal ions such as like Fe2 plus, first you need to think about the electron configuration of the parent atom, and then from there you need to write the electron configuration of the transition ion electron configuration. But if the ion is not a transition metal ion, you should not do like that. But you can directly go into the number of electrons in that ion if it is not a transition metal ion, and then write the electron configuration. So that is the point that need to be highlighted in here.
You could find the total number of electrons in the ion, and then write the configuration based on that. You don't have to write the configuration of the atom and then adjust it for for the ions. It just simply work out that way. But you can do it both ways for these elements. So if you decide to write the electron configuration for the parent atom and then adjust it for the ions, then that's fine. For negatively charged ions, you need to add electrons. For positively charged ions, you need to subtract electrons. So let's start. We need to get up to 18. So we're going to start with 1s. So this is going to be 1s2. And then it's going to be 2s2. After 2s comes 2p, then 3s. So it's 2p6, and then 3s2. So far, we have a total of 12, so we need 6 more. And 3p can hold up to 6, so we're going to stop at 3p6. This is the electron configuration for the chloride ion. For chlorine, it's everything up to 3p5, but for chloride, it's 3p6. You got to add 1 to it.
Okay, so I think now you have some idea about the electron configuration and how we are going to distribute the electrons in these in the electron configuration, and what about a neutral atom, and when it's come to a positive charge ion, how we are going to write the electron configuration, what are the steps that we need to follow, and when it's come to a negatively charged non-transition metal ion, so then what are the steps that need to be taken to write down the electron configuration? So those are some basics of the atom, how the electrons, protons, neutrons are distributed, and how we are going to think about the energy levels and how the electrons are configured inside these atoms. All right. So up to now, is it clear? Anything that you need to clarify, get clarified?
It's clear, madam.
Okay, thank you. So you are back, Harsha. I have asked you some questions during the last slides. Were you with me? And now they are
Yes,
also.
madam. I use it.
Huh? What happened? I hope you are not putting them, just put the thing on and go here and there and do your personal stuff. Okay, you need to please attend the lecture because you need to take the maximum out of the lecture, because I don't know what are the personal things that you have to do. I don't know whether the connections are not good or okay or anything, but just please try your level best to attend the lecture. All right. Okay.
Okay, madam.
Okay, so let's move forward. Okay, so we talk about atoms, electron configurations, the distribution of the protons, electrons, neutrons, everything. And then there need to be another thing. We need to think a little bit about how these electrons are distributed among these energy levels. And when you take two atoms together, they will form a thing called a chemical bonding. These chemical bondings are very much important for us to understand, for us to think about how these atoms or molecules get together to form an nanostructure. So for that, we need to know about specific bondings such as hydrogen bonding, ionic bonding, van der Waals forces, covalent bonding. So likewise, we need to have some idea about those bondings as well. Okay, so the next one, I will show you a little bit about how these ionic bonding and covalent type of a bonding is happening. Okay, so let's see another video, and during the video, I will try to explain it. And also, if you can't understand anything, just let me know, so I will explain this to you. I'm putting videos on this because what I think is, if you can see this video, these will get into your head very clearly rather than doing a kind of like a PO lectures just by showing you the slides. All right. Okay, so let's see how these bonding are also taking place.
Chemical bond.
Okay, so in this video, briefly, it's kind of like a 5-minute video, talks about the bonding, and specifically they will talk about how this ionic bonding and covalent bonding is taking place. All right. Up to now, is the lecture clear to you? Anything that you need to get clarified from me? Whether the videos I'm showing you is not clear to you, the sound is not clear, the things that they explain in the video, if you cannot hear them properly due to the accent that they are using, so just please let me know. Are the videos clear to you? Where's Navodya? She's again gone? Oh. Yeah, I think Navodya might be having a connectivity problem. So these are other videos. Last time also Tisara has this problem, isn't it? I can't hear you. Okay, Tisara, it's okay. I can't. Okay, Tisara, I think your voice is not very clear at all. So I hope if you can put me a message in your chat box and let me know whether the videos are clear to you. Tisara, please put a message on the chat box. Okay, may I ask Lahiru, are the videos clear? The accent and the way that they talk, is it clear, Tisara? Sorry, Lahiru. Okay, so anybody who cannot understand the videos, what they talk about, just please let me know. By the way, just by putting the video, I will also try to explain by myself also the video, what they are telling about. Okay, so let's have a look at this video as well.
Chemical bonding.
Okay, is the video audible? Naveen, is the video audible?
Yes, madam.
Okay. Okay. Okay, Tisara, thank you.
Almost everything we see or touch in our daily life. Chemical bonding. Almost everything we see or touch in our daily life is the result of a chemical bond. The air we breathe, the food we eat.
Okay, so in here they shown you an image of a bread, a slice of a bread. So these breads consist of carbohydrates. So these carbohydrates composed of single atoms, carbon, hydrogen, oxygen, nitrogen, sulfur. They form certain chemical bonds within them, and then they have small level of molecules called as organic molecules, and these organic molecules then again assemble themselves using different types of bonding, and this assembly process has allowed us to come up with these starch or powders. So those could be processed into slices. So that's why they say every matter that we see in our world consists of different types of atoms and different types of bonding. Okay. Okay. I hope no one has. Okay. Okay. Let's see.
Or touch in our daily life is the result of a chemical bond. The air we breathe, the food we eat. The clothes we wear, and so on, are all made up of one or more chemical bonds. The world is generally not composed of isolated atoms. Rather, it is composed of molecules formed as a result of chemical bonds. The strong force that holds together the constituent particles, atoms, ions, or molecules in a chemical species is known as chemical bond. The chemical bonds are broadly classified as ionic bond, and covalent bond.
So in here, they are specifically talking about ionic bond and covalent bonding. So this is the broad classification of the bonding. So there could be subgroups within an ionic bond and a covalent bond, but this is the broad classification. So that is why we are going to learn about what is the type of a ionic bond. What do you mean by an ionic bond? And what do you mean by a covalent bond? So in order to describe that, they might be using certain models, atoms and electrons and energy levels. And let's see how these electrons are paired or shared with each atoms to form either an ionic bond or a covalent bond. Okay. Okay, so in here, just have attention to this part, because now you can see this is the nucleus of an atom. There are two atoms like that, and here it is basically showing you orbital of electrons in energy levels. These might be first energy level, second energy level, and different orbitals that they have in an energy level. There are electrons spinning around the nucleus of the atom. So then depending on the energy levels and depending on the number of atoms, these atoms might be having a certain level of sharing of these electrons with each other, and that is what we call as a chemical bonding. Okay, let's start from here.
Atoms, ions, or molecules in a chemical species is known as chemical bond. The chemical bonds are broadly classified as ionic bond, and covalent bond. Let us discuss these chemical bonds in detail in this module. The bonding which results due to the complete transfer of valence electrons between atoms.
Okay, in here you have heard a term called valence electrons. So what do you mean by a valence electron is, normally for this chemical bonding, always the valency electrons will be participating. Valency electrons are the electrons which are further away from the nucleus of the atom. So why these are called valency electrons? These electrons are not very tightly bonded with the atom. Of course, they are bonded with the nucleus, but the attractive force between the nucleus and the valency electrons are comparatively lesser. When you compare an electron which is orbiting very much near to the nucleus of an atom, the attractive force of that inner electrons to the nucleus is very high. But therefore, these electrons could not be used to make bonding with another atom. But electrons which are further away from the nucleus, which have lesser attractive force between the nucleus, could be participated for the chemical bonding. Okay.
Detail in this module. The bonding which results due to the complete transfer of valence electrons between atoms is called ionic bonding.
Can you see in here, in that so-called ionic bonding, the electrons which were orbiting further away from the nucleus has just transferred that electrons to the other atom. So in here it says the bonding which results due to the complete transfer of valence electrons between atoms is called ionic bonding.
Complete transfer of valence electrons between atoms is called ionic bonding. It is a type of chemical bond that generates two oppositely charged ions.
So now I think it is clear to you. This atom given has donate its furthest away electron to the other atom. So this might be having positive charge because the number of electrons that it had before has been reduced. So the number of protons compared to the number of electrons in these atoms are higher. So it has a positive charge. But when you take the other atom, since it has taken the electron which was given by this atom to here, it is having a comparatively large number of electrons compared to the number of protons it has. So this atom might be having a negative charge. Okay. Let's see how the transferring happens and how the charges are given.
Is called ionic bonding. It is a type of chemical bond that generates two oppositely charged ions. Ionic bonding is observed because metals have few electrons in its outermost orbital. By losing those electrons, these metals can achieve noble gas configuration and satisfy the octet rule.
Okay, so in here they talk about something called metal ions. So for an ionic bonding to take place, most of the time metal atoms are used because it has free electrons and it would rather like to lose its electrons to get a noble gas configuration. Noble gas configuration means all the energy levels are filled up with its suborbital levels. So you all can see in these atoms, there was a single electrons orbiting furthest away to this nucleus. So it does not seems like that electrons belong to that one. It's because if they have only these two energy levels, it will have a noble atom configuration. So most of the time, atoms like to get this noble gas configuration in their energy levels. So that is why they want to lose their electrons rather than keeping them with self. Okay,
Metals have few electrons in its outermost orbital.
metal has few electrons in its outermost orbital level.
By losing those electrons, these metals can achieve noble gas configuration and satisfy the octet rule. Similarly, nonmetals that have close to 8 electrons in its valence shell tend to readily accept electrons to achieve its noble gas configuration.
See, they satisfy each other. There could be metal ions which has electrons freely moving. So they, in order for them to get the noble gas atom configuration, they want to lose their electrons. And also certain metal ions, when they have electrons where they need some more electrons to fill up their energy level, they might be looking for electrons. So when these two get together, the one who will be donating the electron would rather get the noble atom configuration by losing the electron, but the other atom, it will receive the electron and it will get the noble atom electron configuration with that. All right.
Nonmetals that have close to 8 electrons in its valence shell tend to readily accept electrons to achieve its noble gas configuration. In ionic bonding, more than one electron can be donated or received to satisfy the octet rule. Sodium metal has electronic configuration as 2, 8, and 1. It has one electron more than a stable noble gas structure.
So now you know all about what does it mean by 2, 6, 2, 1, 2, 3, 4, yeah, 2, 6, and 1. Okay, we have just learned about how the electron configuration is. So this sodium metal, it has an one electron in the outermost shell.
Sodium metal has electronic configuration as 2, 8, and 1. It has one electron more than a stable noble gas structure. If it gives away that electron, it would become more stable. On the other side, chlorine has electronic configuration as 2, 8, and 7. It has one electron short of a stable noble gas structure. If it could gain an electron, it too would become more stable. Thus, the sodium atom donates its valence electron to achieve stable octet configuration. This creates a positively charged cation due to the loss of electron. The chlorine atom receives one electron to achieve its stable octet configuration. This creates a negatively charged anion due to.
So in here you have heard a term called stable octal configuration. So stable octal configuration means the outermost energy level, they always need to have 8 electrons. So we have just seen we have just observed in the sodium atom, it has 2, 8 and 1. So if we lose 1 electron from the outermost electron energy level, it will be having 8 electrons in the outermost shell. But in the chlorine, it has a certain electron configuration where it has 7 electrons in its outermost energy level. So just by receiving another electron from another atom, it will also be having this 8 number of electrons in its outermost energy level. So that's the noble gas configuration or the octal energy level that they want to have. All right. So let's.
The sodium atom donates its valence electron to achieve stable octet configuration. This creates a positively charged cation due to the loss of electron. The chlorine atom receives one electron to achieve its stable octet configuration. This creates a negatively charged anion due to the addition of one electron. The sodium ions and chloride ions are held together by their strong electronic attractions between the positive and negative charges. Covalent bond.
Okay, so before we move on to the covalent chemical bonds, I think now it is clear to you how they have got these positive and negative charges. What is the reason that the sodium get the positive charge and the chlorine get the negative charge? Why sodium atom wants to lose an electron? Why the chlorine atom needs to receive an electron? And then because of that, they would rather like to have a sodium plus charge and a chlorine minus charge, and by having positive and negative charge, it could be an ionic bond because two opposite ions would like to bond together, so then it will form an ionic bond. So that is the basic principle behind formation of an ionic bond. So let's see how the covalent chemical bonding is taking place.
Between the positive and negative charges. Covalent bonding. A covalent chemical bond results from the sharing of electrons between two atoms with similar electronegativities.
So this is totally different to what we have observed in the ionic bonding. So these covalent chemical bonds result from sharing of electrons, not just by donating electrons, just by sharing electrons. So they share electrons between two atoms which are having similar electron negativity. So that is the main principle behind the covalent chemical bonding. All right.
Covalent chemical bond results from the sharing of electrons between two atoms with similar electronegativities. The electronic configuration of chlorine atom is one electron short of the argon configuration. The formation of the chlorine molecule can be understood in terms of the sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing one electron to the shared pair. In the process, both chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. The dots represent electrons. Such structures are referred to as Lewis dot structures. Thus, the chlorine atoms are joined by a single covalent bond.
Okay, is it clear? This image, this diagram clearly shows how these chlorine atoms get the noble gas octal configuration, which is similar to an argon atom. So for that, they do not donate electrons, but share the electrons. So just by sharing the electrons, what they do is, can you all see this energy level is sharing its electron with the other atom. So then the last energy level would be having the electron configuration of a 8, similar to an argon noble atom. So in here, these specific electrons or points are called as dot. So they have a specific term for that. Let's see what is that.
Such structures are referred to as Lewis dot structure.
Lewis dot structures. So it's based on the person who has discovered this Lewis dot structure, because they are sharing the electrons. Can you all see this energy level and this energy level are sharing this specific single electron, and this energy level of this atom and this energy level of this atom is sharing this electron. So this is the Lewis dot electron configuration structure.
Thus, the chlorine atoms are joined by a single covalent bond. A single covalent bond is formed when one pair of electrons are shared between two atoms.
One pair of electrons, that is 2 electrons. One pair of electrons means 2 electrons are shared between 2 atoms.
It is depicted by a single line between the two atoms. A single covalent bond is formed when one pair of electrons are shared between two atoms. It is depicted by a single line between the two atoms. A double bond is formed when two atoms share two pairs of electrons with each other.
Okay, so now you might be having an idea. We have always seen carbon, double bond, carbon. So this is how the double bonding taking place. So when a single pair of electrons are shared between the two atoms, we represent it by a single line. But when these atoms share 2 electron pairs, so can you all see the carbon atom? It has 2 electrons to share with the oxygen atom, and the oxygen atom is sharing 2 electrons with the carbon atom. So it has 2 electrons pairs. So when they have 2 electrons pairs, we represent it with a double bond. Okay.
Dot structures. Thus, the chlorine atoms are joined by a single covalent bond.
See, a single covalent bond, because it is sharing a single pair of electrons.
A single covalent bond is formed when one pair of electrons are shared between two atoms. It is depicted by a single line between the two atoms. A double bond is formed when two atoms share two pairs of electrons with.
Double bond is formed when 2 electron pairs are shared between 2 atoms.
Each other. It is depicted by two horizontal lines between two atoms in a molecule.
See, you all might have seen these bonds, right? C double bond O. So this is how it represents the covalent bonding.
This type of bond is much stronger than a single bond, but less stable.
It's stronger but less stable. It's strong because it has 2 covalent bonds, but less stable.
Two pairs of electrons with each other. It is depicted by two horizontal lines between two atoms in a molecule. This type of bond is much stronger than a single bond, but less stable. This is due to its greater amount of reactivity compared to a single bond.
Why is it not stable? So in the video itself, it shows why it is not stable, because it has a high reactivity. These two covalent bonds has high reactivity, so it is not a stable structure. It always tries to get connect with some other things, okay, because the reactivity is higher.
This type of bond is much stronger than a single bond, but less stable. This is due to its greater amount of reactivity compared to a single bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. When three pairs of electrons are shared between two atoms in a molecule, a triple bond is formed. It is the least stable out of the three general types of covalent bonds. The two carbon atoms in the ethyne molecule are joined by a triple bond.
Okay, so is this video clear to you? May I play it one more time for you, or is it totally clear? Will you get bored if I play it one time without explaining? Naveen, shall I play the video one more time without explaining, or have you all got everything into your head?
Clear, madam.
Clear. So do I need to play it back? Anybody? Okay, so I hope you got this everything into your head. So now when I share the lecture materials, I will try to share these videos also with you all, so then you can refer them back to have an understanding about how these bonding are taking place. It's because when we proceed further in our lecture, we might be constantly looking at these covalent bonding. What do you mean by a covalent? What is the electron transitions that need to happen during certain bondings and such like that, we will be sharing. Okay, so for today's one, up to now, I need to have some discussion with you, so that I have an idea whether you all have understand what I was teaching about. Is the lecture clear to you? I need an answer from everybody. At least if you all can, if you all can't talk, at least if you all can give me a feedback on the chat box. So Navodaya, are you back? Is the lecture clear to you?
Yes, madam.
Anything that you need to get clarified? Questions? Anything?
No, madam. It's clear.
Okay. So Harsha.
Lecture is clear, madam.
Okay. Harsha. Lahiru. Chat box. Okay. He says it's clear. Naveen.
Clear, madam.
Okay. I think I have lost Tisara again. Might be he's having a unstable connectivity. So now I think after that, what we need to talk about is a little bit about, let's talk a little bit about the bottom-up approach that they use to form these nanostructures. All right. So in that one, actually, what I'm going to do is, so now in here, we need to think about a certain thing called self-assembly, because we have just observed there are two methodologies to fabricate nanostructures. So these nanostructures could be formed using the top-down approach or the bottom-up approach. So in this one, we are going to learn a little bit more about the bottom-up approach for the self-assembling of organic molecules for different dimensional nanostructures. So when we are to talk about the different dimensional structures also, we need to talk about zero-dimensional nanostructures, one-dimensional nanostructures, two-dimensional nanostructures, as well as three-dimensional nanostructures. Okay, so normally a molecule is defined as a sufficiently stable, electronically neutral unit of at least two atoms in a defined arrangement held together by very strong chemical bonds. So now you all know about what an atom is, how the electrons are configured inside an atom, and how these electrons are held together using strong chemical bonds. So a single molecule is called where at least two atoms are there, and these two atoms are in a defined arrangement, definite arrangement, and they are held together by very strong chemical bonds. So that's a single molecule. So these molecules are the basic unit for expressing structures and functions of the material. So these considered as the main building block of a structure. So these structures mainly and how they are designed in the final macro architecture, the design of that molecule, design and the properties, individual properties of these molecules are very important. It because the real properties of the materials are directly related not only to the molecule but also their arrangement way. That means how they get arranged in the macro size scale or the nano size scale. The arrangement matters a lot when we talk about the real properties of the final material. And also it is very important for us to know how small molecules could be assembled together into large entities, because when they assemble into large entities using the bottom-up approach, the way they assemble together will mainly depict their final morphology, whether it is a tubular structure, whether it is a sheet structure, or whether it is a 3D, another globular type of a structure. So not only the morphology, but also the final chemical functional groups that are attached to this final structure due to the presence of single molecules assembled together mainly contributes towards the final properties, physical and chemical properties of the material. So it is very important that how small molecules could be assembled together into their larger entities, and also molecules of sub-nanometer size. That means when these single two atom molecules are get together, and then when they form nanometer size, gather together to form a real macroscopic material at different scales. So these nanometer size molecules, assembled molecules will get together to form the real macroscopic material at different scale. Different scales mean it could be either a micrometer or the macrometer scale. Okay, so normally what happens is in the atomic range or the sub-nano range, atomic range, these atoms will form into a nanoscale, sub-nano to nano. That means from the atomic scale to the nanometer scale, and from the nanometer to the micrometer scale, they will get assembled. And from the micrometer scale to macro scale, they will be having certain agglomeration. So then at each of these scale, there are unique features. So these unique features are very much important for us to know. So then we can talk about the final property of the nanomaterial. Okay. So all these we are talking about the self-assembling of atoms or molecules to form nanostructures. Okay. So the formation of nanostructures or the self-assembly of small molecules into nano-sized nanostructures plays an important role. It is the key for us to understand the molecular interaction and to control or regulate the size, shape, and even the properties of the nanomaterial. So I think this is very much understandable. So for us, it is needed as material developers, we have to understand molecular interaction, and then we need to control these molecular interactions to control or to regulate the size and shape of the final material and even the properties of the final nanomaterial. All right. So the nanomaterials with at least one of the three dimension in the range of 1 to 100 nanometers have been attracting great interest due to the during the past 3 decades, because we all know to define a nanomaterial we need to take the dimension of a normal material. We all know any material has 3 dimension: x direction, y direction, and z direction. So any dimensions, if the size range is between 1 nanometer to 100 nanometer, we define such material as a nanomaterial. So these nanomaterials has attracted a great interest during the past 3 decades. I think we have talked about Richard Feynman and his famous statement about there's plenty room at the bottom in 1959, and after that era, this nanotechnology got popularized and people looked at what are the ways that they can use these nanomaterials in order to come up with very new materials which are very much important for our final applications. All right. So these nanomaterials could be divided into inorganic materials, organic materials, or bio-nanomaterials. So all these depends on its initial atoms. So we all know organic or inorganic. The definition of organic or inorganic means we all know organic materials might be having mainly carbon, hydrogen, nitrogen, sulfur, and oxygen in their chemical moieties. But for the material to be an inorganic material, it might be having silver, copper, tin, titanium, such as non-organic. That means non-carbonous materials are termed as inorganic materials, and carbonous materials are called as organic materials. So not only depending on its carbon content, but also it could be bio-nanomaterials as well, because we all know these living structures are formed by molecular self-assembling process. So that's the main building of forming different biological structures. So normally the nanomaterials are mainly divided into inorganic materials, organic materials, or bio-nanomaterials based on their chemical compositions. And also there could be hybrid nanomaterials. Hybrid nanomaterials mean there could be nanomaterials where you can mix either organic materials or inorganic materials or bio nanomaterials, mix these three together or to combination of two together and make hybrid nanomaterials. So these hybrid nanomaterials composed of mainly inorganic and organic or biological parts. So those are some terms that we need to know about when it's come to the nanomaterials. And when we talk about the self-assembling of these individual molecules or atoms to different dimensional structures. All right. So I think we have talked about how we can come up with different nanostructures at different sizes. So these materials can be fabricated through bottom-up or top-down approach, the nanofabrication. So the bottom-up methodology is particularly useful for the fabrication, specifically the organic materials in which various non-covalent interaction. So we have just talked about covalent interaction. So most of the time when you use the bottom-up approach, there are various non-covalent interaction also have taking place specifically during the self-assembling process. Okay. So inorganic nanomaterials have been mostly investigated from the beginning of the rise of the nanoscience. So that means as a material science area, these nanosciences began in very late 1950, in very late of 1950s, and by that time people have paid more attention on inorganic nanomaterials such as silver nanoparticles, gold nanoparticles, or certain metal alloys. So they have talked about inorganic type nanomaterials. But self-assembly is a process where it is there in our, even in our environment, even our human bodies are made through self-assembling of individual organic molecules. So self-assembled organic or biological nanomaterials, which had a long history, have also been attracting great interest by now. Okay. So now during the next few slides, I will be mainly talking about giving you some examples about how these organic molecules could be self-assembled into nanostructures. Okay. So I think it is now 5 minutes past 1. Can you all bear with me for 10 more minutes? Will it be okay?
Yeah, madam.
Okay. Okay, so if we take these organic molecules, see these organic molecules are one of the most promising candidate to perform self-assembly with different ability, versatility, and also molecular design ability and the tailoring ability. That means you can control the assembling process because these organic molecules might be having different functional groups. So normally when you talk about the self-assemblies, these organic molecules could be composed of lower molecular weight organic molecules or 5 conjugated systems, or it could be macromolecules or polymers, or it could be dendrimers. So these terms you might be hearing these for the first time. So in here, I have mainly given you few examples what a dendrimer means, and you might be all knowing about what a macromolecule or a polymer is. Polymers or macromolecules composed of long chain carbon structures where the chain length or the molecular weight would be very high. And also specifically these organic molecules which are used for the self-assembling to get these different dimensional structures might be having different molecular weights, because we all know these macromolecules, polymers or dendrimers, depending on the size, they might be having a different molecular weight, but still they are the main building block. So these building blocks will be getting like in here in a normal dendrimer to get these different dimensional nanostructures. So even this dendrimer, these dendrimers are formed branching these molecules together. So depending on the branching number, they give a thing called a generation. So it starts from a core where you have a core like in here, and then they might be having surface active groups. So these core and the surface active groups will get into another molecule of a similar manner, and then it will form a generation, the first generation, it will form a certain level of a bonding. So this core get on branching to a certain extent, so it will form a branched structure. So this branched structure, we call it as a dendrimer. So these branching points are the individual atoms or the molecules. So the branching, these complexation or the bonding will take place. So then it will form into these dendrimer structure. So this single dendrimer of a certain molecular weight could be the main building block for a self-assembling process. So then it will get into the nanometer scale structures. And also it says these organic molecules could be having 5 conjugated systems. So what do you mean by 5 conjugated systems? We have already talked about covalent bonding taking place between certain atoms. So in here you can see in this molecule carbon and carbon, it has a covalent bonding. So this covalent bonding, we call it as a conjugation or a 5 configuration. So this system 5 bond. These 5 bonds that we have in here, we can see 2 pi bonds. These 5 bonds are not interacting with each other because they are more apart. So these 5 configurations are not non-conjugated. Non-conjugated means they are not very close. They cannot make chemical interaction between each other. But the molecules that we used in for the self-assembling process could be having 5 conjugated systems. Conjugated systems means these double bonds might be having arranged in these molecules in an alternative manner. So then it could be it can have the interaction between each bonds. So then we call this as a 5 conjugated system. So 5 conjugated system, when you compare non-conjugated and a conjugated system, you can see in the conjugated system, these atoms and molecules are held together because it has a conjugated structure. But in here, if it is the 5 bonds are non-conjugated systems, it has lesser interaction. So for us to make self-assemble nanostructures, this conjugation is very much important. Okay, that is why these organic molecules could be composed of lower molecular weight or organic molecules of high conjugated systems. So this conjugation structure is very much necessary for a molecule for it to assemble into a nanostructure. All right. Actually, by next lecture, I will talk a little bit more about when we do this bottom-up approach, how the self-assembling take place, what are the types of bonding that they use, and then how this interaction happens, and also how we can get different dimensions in our nanostructures. So during the next lecture, we will cover that part. Okay. So up to now, I think I can wind up for today. But before winding up, I want to ask from you again and again anything that is not clear to you. Just ask me if there's anything which is not clear to you. Is everybody okay with the lecture? I will talk with the SLTC and then see how I can share the lecture notes with you. It seems like although I have uploaded the lecture notes and the material, still you have not got it. So that means there should be a methodology. Normally, can one of you tell me now? I think you all have experience getting the lecture notes from other lecturers as well. So I think it is the LMS system that they put the lectures, right? So after putting the lecture, you all can directly go and get the lecture notes, or does the lecturers share any link with you? Naveen? Naveen?
Madam, sometimes we get the lectures from the LMS. Other than some lecturers, they share the lecture notes with our representative, and we get the lecture notes from through him.
Okay, so that means you have an email system, right? So I think Lahiru is the batch representative, isn't it, Lahiru? No, Lahiru can't talk, no, he can only chat. Okay, Lahiru, if you can, yeah, please look into that. At least if you can share the email address of you with me, so then I will email that to you. So please make sure you share the materials with your batchmates, all the batchmates who are participating for the lecture. I mean, like, I don't know how many students are there also, because now I have noted there are 6 students in this lecture, but in the batch it shows 15 or 20 odd number of students, but I haven't seen none of them are taking part in the lecture. Only 6 students are always taking part. So Lahiru, yeah, just give me a call and then please let me know your email address. So then I will share the study material with you where you can share it with your batchmates. All right. Okay, so I hope you have got a very good understanding about these nanostructures and nanomaterials. So we will proceed with the syllabus. So the next lecture, I will talk mainly about a little bit more about the bottom approach and how these bonding are taking place, and then we will go forward after that. Okay, so I thank you all for participating for the lecture. Okay, until we meet next Friday. So have a nice day today. Thank you all.
Thank you, madam.
Thank you, madam. Stay safe.
Thank you, madam.